Theories of light. Now there have been many theories of light over the years, and basically can be broken down in particle or wave theory. In fact, some of the early ideas of light was, one, you had little tendrils coming out of your eyes and they would touch things like that. You had beams of light coming out of your eyes, and once you hit them, you saw that it was even kind of a particle theory where light was bouncing off. Things were bouncing off objects and going to your eyes. Newton put forth a particle theory. He thought, well, other things act like particles, so why not light itself? But it was a wave theory that was the first accepted value. Light is a wave. Christian Huygens, I believe he was a Dane, lived in a port city, would see the waves curving around the structures, the jetties, the breakwaters, and things like that, and did similar experiments with light. Noticed that light did the same thing around analogous structures. He said, well, if waves do this, then light must be a wave. And this was the theory we used for a long time. Light is a wave, and it is a wave. But then we have Einstein. Now, Einstein has something called the photoelectric effect. It's how your little solar panels work, that when light, a particle light, now he coined this phrase, the photon. Photon is like a particle of light. It's energy, it's a packet of energy, but when that packet of energy would hit metal, it had the right energy, would knock off an electron. And so we have a particle, and so light is a particle. Light is also a wave. We call this the dual nature of light. That dual nature of light. Light is a wave, light is a particle. The only thing is we can only use one theory at a time. You can either explain light as a wave, or we explain light as a particle. And some things are easier to explain as a particle, and some things as a wave. We're pretty much going to be using the wave theory. The wave theory, that's what we use today, what we'll be using in this particular chapter. But we have both these theories. It turns out everything has a wave theory. Particles, electrons, they found have this dual nature, that they're a particle outside of the atom, but when they're inside, they act more like energy. Even matter has something called the Broglie wave. Leads us to the speed of light. Now, some of the early measurements by Olaus Rømer. Now, Rømer was an astronomer, and he was looking at the moon Io, the Jupiter moon Io, and he noticed that in certain times of the year, depending on where we were at orbit, that the Io would not appear from behind Jupiter when it should. It would vary in time. He was trying to explain that, and he looked at when we were on different sides of the Earth's orbit, and he, based on the diameter of the Earth's orbit, because we knew that, he figured out that the light must have a finite speed. Up at this time, they thought light was instantaneous. And even Newton tried to measure the speed of light, putting cannons on hills and things like that, just too fast. So people thought it was just instantaneous. It gets produced, boom, it's there. But Rømer decided, well, it must be finite. It must have some sort of finite upper speed. And he said about 300,000 kilometers, which actually wasn't bad. It's kind of where we are now. Which leads us to Albert Michelson. Albert Michelson was the first American to win a Nobel Prize. First American to win a Nobel Prize. And he got it for the speed of light. And he used spinning mirrors. Now, this is a later experiment. Actually, the first experiment was done at the Naval Academy. That's where Albert Michelson was a professor at that time. And a much smaller thing, about 100 yards on that. But the idea here with the spinning mirrors is that the light, to bounce off one mirror and hit this mirror and get back in the eye, the little octagonal mirror has to actually rotate a little bit. In other words, it can't just sit still and it bounces in the telescope. It doesn't work that way. It actually has to move a little bit. So they would spin this very fast. If it's spinning too fast, you get on one side. Spinning too slow, you don't see it. If it's spinning just right, and based on how much it's spinning and things like that, they can get the speed of light. And the thing about the speed of light is a constant. Light travels at one and only one speed. It only travels at the speed of light, no faster, no slower, no matter what. There's no what ifs, because this is the way the universe works. Light travels at only one speed, and only light can travel at the speed of light. Only light. Nothing else can travel at the speed of light except light. All light travels at the speed of light. It's such a special speed, we give it its own symbol of a lowercase c, and like all other velocities, it's a meter per second. And so c, the accepted value, the current best value for c is 2.999979 times 10 to the 8th meters per second, and we approximate that to be 3 times 10 to the 8th meters per second, or 300,000 kilometers per second. Remember Romer? Romer said it was about 300,000 kilometers per second, so he did pretty good. He did pretty good for himself on that. But what is light? Now, light is energy. It is energy, and it's by extent to electrical charges. And whether you use the particle theory, which is kind of the Bohr atom. Some of you have had chemistry, studied the Bohr atom, where an electron drops from a higher energy level to a lower energy level, and it spits out a photon. This is the Bohr atom. This is part of modern physics. Or the wave theory, where you have an electron, excited electrons. These excited electrons emit electromagnetic waves on that. But either way, you have moving electrons. Bohr atom, you have moving electrons. Wave theory, moving electrons. But electromagnetic waves, now, they are transverse waves. Keep in mind, these are transverse waves. But there are two waves. Two waves here. You have an electrical wave and a magnetic wave at right angles to each other. That's why they do not need a medium. It's the only wave that doesn't need a medium, because they're two waves and they're self-propagating. Remember, we did some of our readings about, we had Oersted. Remember, the moving electron. The moving electron created a magnetic field. So a moving electrical field is going to create a moving magnetic field. And we talked about Faraday. Faraday said a moving magnetic field has a moving electrical field. We put these two ideas together. A guy named Maxwell put these two ideas together to create the electromagnetic wave. So that moving electrical field makes a moving magnetic field at a right angle. That moving magnetic field creates a moving electrical field. So we say it's self-propagating. There's self-reinforcing waves on that. And in our spectrum, so we have the electromagnetic spectrum here. This entire spectrum of light from radio down to X-rays. And so I got a little thing for you here.
Electromagnetic spectrum is just a range of radiation. Let me tell you what they are. Radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays. From the TV station to your living room, that is the work of radio waves. Heating food in just seconds, microwaves do that. Heat treatment for illness, take pictures in the dark. They are even in your remote control. Infrared radiation, the electromagnetic spectrum is just a name of a range of radiation. Let me tell you what they are. Radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays. Red, orange, yellow, green, blue, indigo, violet. That is the only part of the spectrum that can be seen by us. The suntan on your skin through bacteria and viruses used to detect forgery. That is ultraviolet. The electromagnetic spectrum is just a name of a range of radiation. Let me tell you what they are. Radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays. see your broken bones and your hidden bonds. That is the work of X-rays. Cure cancer cells and sterilize. Dangerous gamma rays do that. Now we have completed the electromagnetic spectrum. If you still do not understand, then play the song again. The electromagnetic spectrum is just a name of a range of radiation. Let me tell you what they are. Radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays, radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays.